Hello everyone, I'm Rahul, a PhD student at University of Illinois at Urbana-Champaign, and I'm going to present our work on power, performance, and image quality trade-offs in foveated rendering. As XR gets more popular, we are realizing that there is an orders of magnitude gap between power, performance, and quality of the current headsets and the desired headset. Even though modern headsets like PSVR 2 can render high-quality scenes like shown here, they are tethered headsets. An ideal headset would be lightweight, tetherless, and low power and low energy. One of the bottlenecks in achieving this with high-quality graphics is rendering. So why is rendering expensive? This is because increasing resolution of displays, high frame requirement, and multiple views for XR. With strict power and weight budget of a tetherless headset, the system design gets even more challenging. Foveated rendering is one of the techniques that have been suggested to reduce this cost. The idea is to track users' gaze and render the fovea region with high resolution while decreasing the resolution in steps as we move away from the fovea. So even though foveated rendering saves energy, it requires gaze tracking, which adds additional energy of its own. Other than that, there are design complexities because of strict motion to photon latency. A simplified version is fixed foveated rendering, where we assume that the user always looks in the center of the screen, thus removing the gaze tracker and the associated overheads and latency constraint. But now we need a larger fovea to maintain the quality, increasing the rendering energy. And still, if the user looks on the side, the quality is compromised. So the trade-offs are TFR provides better quality, but has lower energy savings because of the gaze tracker. And the FFR has high energy savings because there is no gaze tracker, but the quality is also low. For a mobile headset, energy is a big concern. So state-of-the-art TFR often loses to FFR at the cost of quality. But if we want great graphics in mobile headsets, we need to do better. Can we have TFR quality with more energy savings than FFR? Yes, we can. That's where we propose our design. We provide better energy savings and good quality, beating both state-of-the-art TFR and FFR. So how do we do this? So this is what a track foveated rendering pipeline looks like, where the gaze is tracked through a DNN and then provided to TFR. We approximate the gaze tracker, which reduces the energy, but also causes error in the gaze. This results in an overall quality loss. We mitigate it by carefully increasing the fovea radius based on the gaze error. The end result is that for our co-designed TFR, both energy and quality are better than the state of the art. So let's take a look at our contributions. First, we quantify the TFR and FFR energy and show that state-of-the-art TFR loses to FFR in terms of energy. The rendering energy in case of TFR is lower than FFR, which is a good thing. But when added with the cost of the gaze tracker, the total energy is higher than FFR by more than 1.2x. We propose a novel approach to co-design TFR and the gaze tracker. Finally, we compare this design with state-of-the-art TFR and FFR and show that our technique achieves better quality at lower energy than FFR. Our work is a step to make complex graphics possible on future mobile headsets. So let's quickly go through our evaluation platform. We use 4 scenes that are a mixture of indoor and outdoor: Bistro, Classroom, Sponza, and San Miguel. We use NVIDIA's VRS for foveated rendering, where we can divide the frame in 3 shading rates, where the center is highest resolution and periphery is the lowest resolution. It allows us to change the sizes of these regions, including their shading rates. Our quality metric outputs a GOD number on a scale of 10, where a difference of 1 means 75% of the observers can tell the difference between reference and a test image. So we select 9 out of 10 as an acceptable quality. For our hardware setup, we use RTX 3090 and Intel i9. Our gaze tracker is RIT-Net plus DeepFox gaze estimation, which is tested on an additional hardware that is Jetson Xavier. So how do we compare TFR and FFR? We first need an optimal foveation configuration for both, and this is defined as the lowest energy configuration, which provides an acceptable quality. We compare both TFR and FFR generated frames with a reference frame while providing the quality metric with the accurate gaze. We vary the rendering parameters while maintaining a GOD value of greater than 9. This gives us optimal configuration for both TFR and FFR. Next, we measure energy for both techniques. Here, we show TFR energy as a percentage of FFR energy. And as you can see in 2 out of 4 cases, TFR energy is lower than FFR energy. This is because TFR needs a smaller fovea radius. In 2 cases, however, we don't see any energy difference as the foveation configurations are same. Why? This is because even though we can visually tell the difference between the images, The quality metric is indifferent to TFR and FFR for certain scenes, requiring the need for a better quality metric. Next, we add the gaze tracking energy, which makes the end-to-end TFR more expensive than FFR. So the question is, how do we improve the gaze tracker? So our goal here is to maintain the latency less than 15 milliseconds while minimizing the gaze tracker energy cost as much as possible. We explain the rationale of 15 milliseconds in the paper. We approximate the gaze tracker using structured pruning. The idea is to remove the feature maps with the lowest sum of weights and retrain the network to regain the quality. We also use image downsampling in combination with pruning. So let's take a look at latency and energy numbers. On the x-axis, we have different pruning levels, and the y-axis represents the latency. With increasing pruning levels, the latency drops. And as we decrease the input size, the latency drops further. The total possible speedup is greater than 25x, while the total energy savings is more than 50x. When we add the latency constraints here, we notice that pruning alone is not enough. So why don't we go with maximum pruning and minimum size? And this is because we haven't looked at the errors yet. The bar represents the percentage of cases with degree error less than 5 for the size 256 by 160. The shaded bar represents a smaller input image size. Higher the bar, better is the quality. And even without pruning, we notice that the shaded bar has poor quality. So the degree error is higher for 128 by 80 input. Looking at the latency, the acceptable configuration is the size 256 by 160 and pruning levels of 98 to 99.5%. With these, we get a speedup of 9x and an energy saving of 20x. Still, there are gaze errors, so how do we handle them? We first test if TFR is robust to the errors in gaze tracker and then how to mitigate the end-to-end quality loss. We provide the TFR with approximated gaze, but we provide the ground truth gaze to the quality metric. And then we check if the GOD is still acceptable. So let's take a look at the end-to-end quality. On the x-axis, we have different scenes and different gaze sequences. The red line denotes the acceptable quality, and all the bars need to be above the red line to be of acceptable quality. For the most part, GOD is acceptable except some cases in bistro. We need cheap mitigation for this, and so we tried different schemes. But the cheapest mitigation is by increasing the middle radius, which is the green part, until the GOD is above 9. The effect of this mitigation on performance and energy is less than 1%. Comparing our co-designed TFR with FFR, we notice that our proposed design consumes less total energy than FFR. We again notice that San Miguel and Classroom are exceptions, and as mentioned before, this is because the quality metric is indifferent to FFR and TFR for these two scenes. So in conclusion, we show that state-of-the-art TFR loses to FFR, but through our co-designed TFR, it is possible to achieve both high energy savings and good quality. Our co-design is a step to make more complex graphics possible on future mobile headsets. Thank you for listening to our talk. For more details, you can read our paper. Now we'll take some questions.